Somewhere along the cold edge of Lake Superior, if you know where to look, the ground is full of holes. Not random ones, not erosion, not collapsed animal burrows, deliberate excavations, ancient pits and trenches cut into rock that contain some of the purest copper found anywhere on Earth. Thousands of them. Some shallow, some running several feet deep, scattered across the Keweenaw Peninsula and the nearby Isle Royale, in a pattern that speaks clearly of organised, repeated, intentional work. Work that began a very long time ago. And when you start doing the math on how much copper was pulled out of the ground, the numbers get strange. Strange enough that people have been arguing about what they mean for well over a century. That's where we're starting tonight. If you're using this to fall asleep, that is exactly the reason I make these. So subscribe if you haven't, and tell me in the comments where you are and what time it is right now. I genuinely read them. It's one of the things I look forward to. People listening from small towns in Norway, from apartments in Tokyo, from bedrooms in Sao Paulo at 3 a.m. There's something quietly wonderful about that. And if you want to listen without ads, without background music, just the voice and the story, you can follow the show on Spotify. Ad-free, music-free. The link is in the description. Now, back to the shoreline. Here is the question that sits at the centre of everything we're going to explore tonight. Archaeologists have documented enormous evidence of ancient copper mining around Lake Superior. The scale is not in serious dispute. The pits are real, the tools are real, the dates are real, and they stretch back thousands of years. But somewhere between the raw evidence and the popular story about this place, things get complicated. Claims circulate that somewhere between 500,000 and 1 billion tons of copper were extracted from these mines in prehistoric times, that the copper simply vanished, that nobody knows where it went, and the implication, sometimes stated directly, sometimes hovering just beneath the surface, is that something or someone took it somewhere far away, maybe across the Atlantic, maybe to fuel the Bronze Age civilizations of the Mediterranean world. It's a compelling story. It has the shape of a great mystery, and parts of it are genuinely mysterious. But some of those numbers and some of those conclusions rest on much shakier ground than the people repeating them tend to acknowledge, and that's actually what makes this worth exploring carefully. Because the real story, the one that archaeology has been slowly and patiently assembling for decades, is remarkable on its own terms. It doesn't need embellishment. It involves indigenous cultures whose sophistication and reach we're only beginning to understand fully. It involves ancient trade networks stretching across a continent. It involves copper objects found thousands of miles from where the metal was mined. And it involves questions that remain genuinely open. Questions that serious researchers are still working on, without needing to reach for explanations that skip over the evidence. So tonight we're going to take it slowly. We'll look at where the copper is, why it's extraordinary, and how people first started working it. We'll look at the archaeological record for what is sometimes called the Old Copper Complex, one of the oldest known metalworking traditions anywhere in the world. We'll look at what the mines themselves actually look like, and how researchers figure out how old they are. We'll try to get an honest sense of scale, because the real numbers are striking enough without inflation. And then we'll sit with the genuinely open questions. Where did the copper go? How far did it travel? What can the chemistry of ancient artifacts actually tell us? And what can't it tell us yet? We'll look at why some researchers draw comparisons to the Bronze Age, what those comparisons are worth, and where they fall apart. And we'll look at how this whole subject picked up a layer of legend and speculation in the 19th century that has been sticking to it ever since, sometimes obscuring more than it reveals. What I want you to leave with, if you're still awake by the end, is a clear sense of what the evidence actually supports, where the ground is solid, where it gets soft, and where there are real mysteries worth holding on to, not because they point to anything sensational, but because the honest unknown is more interesting than a false certainty in either direction. There's a version of this story that gets told in a kind of urgent, breathless way, as if the establishment is hiding something, as if the only explanation big enough for the mystery is a lost civilization or transoceanic visitors. I'm not going to tell you that version, not because it isn't fun, but because I think the real version, the one with indigenous metalworkers operating across a continent thousands of years before anyone in Europe was doing anything comparable, is more astonishing, more human, and more worth understanding. So settle in, get comfortable. The lake is cold and dark and very old, and somewhere beneath its shoreline the ground still holds its secrets close. Let's start with the copper itself. Lake Superior is the largest freshwater lake in the world by surface area. It holds about 10% of all the surface freshwater on Earth. It is cold enough in deep water to preserve wooden shipwrecks almost indefinitely. It generates its own weather systems. Sailors have feared it for as long as sailors have been on it. And along its northern and western shores, and on the islands that rise from its surface, there is something in the bedrock that exists almost nowhere else on Earth in comparable abundance. Native copper, not copper ore. Not copper mixed into rock that has to be smelted and refined and chemically coaxed into a usable form. Actual metallic copper, already in its pure state, already workable, already there. Sitting in veins and pockets and loose pieces scattered across the ground like an invitation. That distinction is worth slowing down on, because it's central to everything that follows. Most copper in the world exists as ore. It's chemically bonded to other minerals, locked inside sulfides and carbonates and oxides, blended into rock in concentrations that might be 2 or 3% copper by weight on a good day. To get usable copper from ore, you have to crush the rock, apply intense heat, manage chemical reactions, deal with slag, and repeat the process in sophisticated ways. This is smelting. It requires furnaces, fuel management, and a body of technical knowledge that took human civilizations a long time to develop. When we talk about the Bronze Age in the Old World, we're talking about cultures that had worked out how to do this, at scale, over long periods of time. Native copper skips most of that. It forms through geological processes that are relatively rare, and it exists in the metallic state naturally without any smelting required. You find it, you work it. The Lake Superior region has more of it, in more accessible concentrations, than almost anywhere else ever documented on Earth. The two places at the heart of this story are the Keweenaw Peninsula and Isle Royale. The Keweenaw is a long finger of land that juts into Lake Superior from the upper peninsula of Michigan, pointing northeast toward the open water. It's narrow and rugged and heavily forested, and beneath its surface runs a geological formation that has been attracting human attention for a very long time. Isle Royale is an island about 45 miles offshore, now a national park, remote enough that it sees relatively few visitors even today. Between these two locations, the copper is concentrated in a way that, once you know about it, is difficult to think of as anything other than extraordinary. The geology behind it is old, much older than human presence in the region. About 1 billion years ago, a massive rift opened in the middle of what is now North America. The continent was trying to tear itself apart. Enormous quantities of basalt lava poured out through the rift over millions of years, building up a thick sequence of volcanic rock. Then the rifting stopped, and the rock layers slowly subsided. Hydrothermal fluids, hot mineral-rich water circulating through the crust, carried copper through the rock and deposited it in veins, in cavities, in the spaces between basalt flows. Over geologic time, copper accumulated in those formations in concentrations and in forms that are essentially unique. Then the glaciers came. The repeated glaciation of the region during the ice ages did something useful from a human perspective. Glaciers are effective at erosion. They scrape and grind and carry. As they moved across the Keweenaw and Isle Royale, they removed overlying rock, exposing the copper-bearing formations at or near the surface. They also broke off pieces of copper and carried them south and east, scattering what geologists call float copper across the landscape far from its source. A traveller in the region thousands of years ago would have encountered copper not just in veins in bedrock, but in loose chunks sitting in the soil on the surface of the ground, along creek beds and shorelines, tumbled out of their original context by glacial transport. This created two essentially different types of workable copper in the region. There is vein copper, which is copper still embedded in or closely associated with its host rock, typically found by digging into the bedrock formations themselves. And there is float copper, which is material the glaciers liberated and redistributed, sometimes as small pieces, sometimes as enormous masses, found scattered across a much wider area. The largest single piece of native copper ever documented in the region weighed something in the neighbourhood of 6 tons. Though float copper could range from that kind of spectacular mass down to small nodules the size of a fist or smaller. Both types were available to ancient people. Both left traces in the archaeological record, though in different ways. The vein deposits required actual mining to access. You had to remove the host rock to get at the copper. This is where the ancient pits come in, the ones I mentioned at the beginning. Those excavations cluster along the Keweenaw and on Isle Royale precisely because that's where the bedrock formations are richest and most accessible after glacial exposure. The work involved in creating those pits was not casual or accidental. It was purposeful, and it was repeated over long periods of time by people who knew what they were looking for and knew how to get it. Float copper was more immediately accessible. You could pick it up without any excavation, and the glaciers moved it broadly enough that people across a significant portion of the Great Lakes and Midwest region would have encountered it without necessarily making any connection to its source. A piece of copper sitting in a creek bed in Illinois or Wisconsin might have been carried there by ice from a formation in the Keweenaw. Someone discovering that piece would have had no obvious reason to know it was anything other than a local resource. This is one of the things that makes the regional picture complicated when you try to trace how copper use spread, and we'll come back to that later. For now, what matters is the basic character of what the region offers. Native copper that can be hammered cold into shapes, that work hardens under repeated hammering and softens again with gentle heating, that can be formed into points and hooks and blades and ornaments without any smelting, without any furnaces, without any of the infrastructure that Old World metallurgy eventually required. The barrier to entry was low in a way that has no real parallel in most of the world's copper-producing regions. That accessibility invites both ancient use and modern misunderstanding. It invites ancient use because the material rewards engagement. If you find native copper and you start working it, it behaves in ways that encourage further experimentation. It doesn't require a technological breakthrough to start using. The breakthrough is in recognizing what it is and developing the skills to shape it intentionally. And both of those things are achievements, significant ones, but they don't require the entire complex of knowledge that smelting demands. It invites modern misunderstanding because the same accessibility that made it available to ancient people makes it easy to underestimate the sophistication involved in working it systematically at scale. There's a tendency, sometimes, to assume that because native copper doesn't require smelting, using it was simple or primitive, something any passerby might have done without much thought. The archaeological record argues strongly against that. What happened here was not opportunistic dabbling. It was organized, technically skilled, sustained over millennia, and connected to social and economic systems of considerable complexity. There's also a tendency, on the opposite end, to assume that the scale of what happened here must imply some external explanation. Surely this much copper required more sophisticated people than we know about. Surely someone must have come from somewhere else to extract it. That assumption also runs into problems with the actual evidence, but we'll work through that carefully. For now, just hold the picture. A cold lake, enormous and dark, a peninsula and an island pushing up out of the water. Bedrock that has been scraped and polished by ice until some of its richest seams are exposed or nearly so. Loose copper scattered across the landscape, glacial debris from 1 billion years of accumulation. And somewhere, at some point deep in time, people finding it, picking it up, turning it over in their hands, starting to understand what it could become. That's where the story actually begins. Not with mystery, not with questions about lost civilizations, but with human curiosity meeting an unusual landscape in a very particular way. The mystery comes later, and it's a real one. But it grows from this ground. Literally from this ground. And the ground is worth understanding clearly before we start asking what was taken from it. If you've spent your whole life around stone, copper's going to feel like a magic trick. You hit a rock with another rock, and it breaks. It flakes, it shatters, it fractures along predictable lines if you're skilled, but it never stops being brittle. You can't push it very far without it reminding you what it is. Copper is different. You hit it, and instead of shattering, it moves. Not freely, not like clay. It pushes back. But if you strike it again and again, patiently it flows under the blows. A lump becomes a bar becomes a blade, the edge thins, the curve straightens, the metal remembers every hammer stroke. This is cold hammering, and it's the foundation of early copper working in the Lake Superior region. No furnace, no crucible, no liquid metal, just native copper and impact. But metal has its own kind of fatigue. As you hammer copper, it work hardens. The atoms get nudged out of their original positions. The material becomes stiffer, less willing to move, more likely to crack if you force it. If you keep going, eventually the piece might snap along a line of weakness, reminding you that copper has limits too. There's a way around that, and it's another piece of knowledge that had to be learned and refined, probably over generations. If you heat the copper gently, to a dull red, or even lower, and then let it cool slowly, the metal softens again. The internal stresses relax. The crystal structure resets. This process is called annealing. It lets you start the hammering cycle over with a more malleable piece. So the craft of working native copper in this region is a dance between hammering and annealing. Shape, harden, soften, shape again. You don't need smelting, but you do need control over fire, attention to colour and temperature, and a felt sense of how the metal is behaving under your tools. Archaeologists see the traces of this in the objects that survive. Imagine a copper spear point from the old copper complex, which we'll talk about in more detail later. Under magnification, its surface is not smooth. It's covered with tiny flattened facets, the ghosts of individual hammer blows. The cross-section might be lenticular, thick in the middle, tapering to a hammered edge. If the maker polished it, those hammer marks are softened but not erased. If they didn't, the texture is more obvious, almost pebbled. Sometimes the starting material betrays itself. A tool made from float copper might have residual curves or irregularities that reflect the original nodule. A piece cut from a vein mass might show flatter initial faces where it was separated from the parent chunk. The techniques weren't limited to simple pounding. Pecking, repeatedly striking with a harder stone in a controlled way, was used to rough out shapes and remove material. After that came more refined hammering with smoother stones or specialized hammerstones, then polishing with abrasives, sand, fine-grained rocks, perhaps leather with grit. Each stage leaves its own signature in the metal, and crucially, early copper work wasn't just about getting to a final shape once. Copper can be reheated, reshaped, sharpened, re-edged. A broken point can be shortened and turned into a new tool. A bent awl can be straightened. A large ornament can be cut down into smaller pieces if circumstances demand it. That reworkability has two big consequences for how we understand this story. First, it blurs the line between tool and raw material. A copper object isn't just made and then used until it's discarded. It's part of a continuing cycle. Today it's a knife. In a generation it might be half a knife and two small awls. A century later its metal might be in a bead, or the blade of a ritual knife, or a small chisel used to work bone or antler. Second, it distorts the archaeological record. When metal is scarce and valued, people don't casually throw it away. They keep it in circulation as long as possible. When something breaks, they fix it or melt part of it down, or in the case of native copper, just hammer it into a new form. So instead of huge middens full of discarded copper, what we tend to find are the things that escape the recycling loop. Items lost in the ground, offerings placed intentionally, pieces deposited in circumstances that remove them from everyday reuse. The range of objects that do survive tells us something about how copper was valued. On the utilitarian side, you get spear points, knives, awls, fish hooks, harpoon heads, woodworking tools, occasionally axes and adzes. These are things that clearly did work. Edges are worn, tips are blunted or resharpened, surfaces are dinged and abraded. Some show patterns of repeated repair, shortened blades, reground profiles that suggest long service lives. Then you get items that don't make as much sense if you think only in terms of pure practicality. Beads, tubes, pendants, conical points that look too delicate for real hunting use, flat sheets shaped into symbolic forms, large, thinly hammered blades that would be fragile under hard use but striking as display pieces. Those start to live in a different category. Ornament, status object, ceremonial item, heirloom. Not strictly non-functional, a pendant can still signal identity, alliance, achievement, but functional in the social and symbolic sense rather than the purely mechanical one. The workmanship often differs too. A basic fishing hook needs to work more than it needs to shine. A ceremonial blade or a prestige ornament might be polished to a high luster, edges crisp, surfaces carefully finished. Sometimes the same technical knowledge is being pushed to a different end. Instead of maximizing durability, the goal might be to maximize visual impact, or to echo a traditional shape in another material, stone, bone, shell, now reimagined in copper. Over time, this creates a layered world of copper things. Some are tools that circulate within a household or a small group, repaired until they're almost more repair than our original object. Others are pieces that move along broader social currents. This is where the idea of long-lived objects really matters. Because copper is reworkable, certain pieces can plausibly remain in circulation for generations. A large, high-quality lump of metal might enter the world as a tool made by one person, then be reshaped into a new form by their grandchildren, then traded away, then reworked again hundreds of miles from where it started. The material identity persists even as the form changes. Some artifacts show wear patterns and reworking that suggest exactly this kind of extended life. A blade that has been reshaped multiple times, a perforated ornament that began as something else, a thick, odd-shaped piece that feels like a scrap, until you realize it might be the exhausted remnant of many previous tools, the last usable core being eked out. And alongside these continuously recycled pieces, there's a different kind of longevity, objects that are taken out of circulation deliberately, copper tools or ornaments placed in burials, items cached in pits and never retrieved, offerings left in wetlands or beneath rocks. These are the things that reach us as intact clues, instead of as raw material for the next generation's tool-making. So when we look at a small collection of surviving artifacts and try to imagine hundreds of thousands of tons of copper being mined, we're looking at the tip of something that was constantly being melted metaphorically back into itself through hammering and annealing and reshaping. The people around Lake Superior weren't just hitting rocks with other rocks. They were learning a new behaviour of matter and building a culture around it, a culture in which metal could be both knife and necklace, everyday tool and sacred object, perishable form and enduring substance. And as copper objects began to move, between individuals, between families, between communities, the metal itself started to trace pathways across the landscape that we can still faintly detect, even when the original tools are long gone. Those pathways are where the old copper complex comes into focus, and where the story turns from local craft to regional phenomenon. Archaeologists needed a name for that regional phenomenon, for this whole web of people and practices orbiting around native copper. The label they settled on is the old copper complex. Complex here doesn't mean complicated in the everyday sense. It's a technical word for a package of behaviours and objects that tend to show up together in space and time. In this case, it's a tradition centred in the western Great Lakes, around Lake Superior, but also into Wisconsin, Michigan, Minnesota and Ontario, where people were mining, working, and circulating native copper on a scale we don't really see anywhere else in North America during that period. It's not a culture in the sense of a single tribe or nation. It's more like a shared language of tools and techniques that different indigenous groups participated in over thousands of years. If you were to hold a typical toolkit from this old copper world in your hands, you'd feel that range immediately. Some pieces are small and unassuming, awls for example. Slender copper points, sometimes with a slightly thickened butt where a handle of wood or bone might have been attached, or just held directly in the hand. These were the everyday multi-tools of their time, used to pierce leather, score bone, punch holes in bark, maybe even as fine drills. Many are heavily worn, tips rounded off and then resharpened, their length slowly retreating under generations of use. Then you'd find points. Some are clearly meant as projectile tips, narrow, leaf-shaped, beveled to accept a shaft, the edges hammered down to a fine, functional sharpness. Others are stouter, more like socketless spearheads or knives, with shoulders or tangs designed for hafting. A few are larger than they strictly need to be for practical hunting, thin and broad and maybe a little fragile, drifting toward the symbolic. Fish hooks are another hallmark. Bent from hammered strip or wire-like rods of copper, they range from tiny, finicky pieces that look suited for small fish to more robust hooks that could have anchored a substantial line. Their shapes echo the same forms known in bone and antler, J-shaped curves, barbs, eyelets. The copper versions don't overturn the fishing tradition, they plug into it. Woodworking tools show up too. Adzes, blades mounted at right angles to a handle for planing and hollowing wood, appear in copper, sometimes in forms that would be instantly recognizable to any woodworker today. The working edge is thick and sturdy, the butt flattened or grooved for lashing. These were the tools that could carve out dugout canoes, shape house posts, hollow bowls. Celts are a little more abstract in name, but very concrete in form. Ungrooved axe-like tools, symmetrical in cross-section, often lenticular or oval, meant to be hafted by splitting a wooden handle and wedging the blade in. In stone traditions, Celts are all over the place. In old copper, their metal equivalents sit right alongside them. Some are robust and clearly built to take impact. Others are surprisingly thin, maybe more prestige item than workhorse. Together, these artifacts map out a world where copper wasn't just for show. It penetrated the fabric of daily life, hunting, fishing, hideworking, woodworking, while also stepping into the arenas of adornment and ceremony. The puzzle is that we almost never catch people in the act of making these things. What we mostly see are finished tools and the occasional misstrike, a broken blank, a discarded offcut. So how do archaeologists get from scattered tools to a story about mining and production? One way is by looking at density and distribution. In certain areas close to known copper sources, you'll find sites where the number of copper artifacts spikes. Not just a stray awl here or a single bead there, but clusters of preforms, roughly shaped pieces that were clearly on their way to becoming tools, and standardized blanks that could be finished later. Those concentrations, especially when paired with hammerstones and anvil stones bearing copper smears, look a lot like workshop debris. Farther away from the bedrock lodes and big float deposits, the pattern changes. Copper becomes rarer, and the pieces you do find tend to be finished tools and ornaments, not half-formed blanks. That gradient. Lots of manufacturing traces near the source, mostly final products at a distance, is what you see in many pre-industrial craft and trade systems. There's also the problem of raw material. Lake Superior native copper has particular trace element fingerprints. When you analyse artefacts chemically and they keep pointing back to the same general geological sources, even if the artefacts are found hundreds of miles apart, it strengthens the idea of organised extraction and wide distribution. Time adds another layer of complexity. When we say old copper complex, we're mostly talking about a window that starts somewhere around 6000 BCE and runs, in various ways and places, until maybe 1000 BCE or a bit later. But those are broad brushstrokes. The exact dates shift from site to site, depending on what's been preserved and which dating methods are available. If a copper tool turns up in a burial with organic materials, we can radiocarbon date. The wood of a handle, the textile of a wrapping, charcoal from a grave pit. We get a more precise anchor. If it's in a layer with other datable materials, we infer its age from context. In other cases, especially older finds from 19th and early 20th century collecting, the provenance can be frustratingly vague, and the dates become more of a best estimate than a firm number. What emerges is not a single copper age that starts one year and ends another, but a slowly shifting landscape. People experimented with copper, adopted it intensely in some regions and periods, then, intriguingly, seemed to have scaled back the heavy utilitarian use in later millennia, favouring smaller ornaments and occasional tools. The reasons for that change are still debated. Through all of this, one thing is clear: none of it is an accident, and none of it needs outsiders to explain it. The old copper complex is indigenous innovation, full stop. It's the result of generations of observation, experiment and tradition among the ancestors of native nations in the Great Lakes. They noticed a strange, heavy stone that behaved differently when struck. They learned to shape it, to soften it with fire, to fit it into existing tool traditions and social meanings. They developed local mining methods appropriate to their environment and needs. Later myths sometimes treat these mines and tools as anomalies, as if they're out of place in North America, as if copper working at this scale must have been imported from far away. But when you look closely at the artifacts and their contexts, what you see is continuity. Copper versions of familiar tools, copper ornaments that echo pre-existing styles in bone, shell and stone, copper technology that grows organically out of earlier practices. The mystery isn't, who could possibly have done this? We know who did it. The open questions are about scale, organisation, and change over time, and those questions get sharper when we turn from the tools themselves to the places where the metal was actually extracted. To understand how big this tradition really was, and why it's inspired so many later stories, we have to walk up to the pits and trenches and scarred bedrock of the ancient mines and ask what they can still tell us. If you hike into the copper districts today, you don't find underground cathedrals of worked rock, endless galleries with soot-black ceilings and wheelbarrow tracks. What you mostly find, if you know how to look, are subtler scars. Start with the pits. They're often shallow depressions in the forest floor, sometimes just a few meters across, sometimes stretching into elongated basins strung along an outcrop. In some well-preserved areas, you can walk through patchworks of these hollows, dozens, even hundreds, separated by narrow ridges and low mounds. To an untrained eye, they might look like random windthrow holes where trees once toppled and rotted away. To an archaeologist, the pattern is the giveaway. The pits tend to line up along specific bands of bedrock, following the same geological veins where native copper concentrates. They aren't evenly scattered. They cluster over the sweetest spots in the ore. Between and beside them, you often get trenches. These are longer cuts into the rock, sometimes shallow and diffuse, sometimes more sharply defined. Imagine a chain of overlapping pits that gradually merged as people followed a copper seam sideways along the surface. Over centuries, that activity turns into a trench, a sinuous channel where the overburden has been stripped away and the upper bedrock broken and pried. The material that came out of those pits and trenches had to go somewhere, and that's where the spoil piles come in. If you stand on the right knoll and look around, you can see low, linear mounds flanking the depressions, heaps of broken rock, weathered soil and discarded rubble. These aren't random glacial features. They mirror the shape of the excavations they came from. Early mine operators were doing the same thing modern miners do in principle, moving the unwanted material just far enough out of the way to get at the valuable stuff. Scattered through and around all this are the tools. One of the clearest signatures of old copper mining isn't copper at all, it's stone. Hammerstones show up in dense concentrations, rounded cobbles, often of hard igneous rock, with battered mushroomed ends where they struck again and again against bedrock and boulders. Sometimes they're found in clusters, almost like tool caches. Sometimes they're so abundant you can pick up one after another, each with its own history of blows. These sites mark a big shift from simply collecting float copper. Surface float, loose chunks of native copper dropped by glaciers, can be picked up or pried from boulders with relatively little effort. You still need tools and skill, but the metal is essentially sitting there. Bedrock extraction is something else altogether. It means following copper directly in the rock it formed in, stripping off soil and vegetation, breaking into the host rock itself, and patiently working down along a vein. Archaeologists can see that difference in the architecture of the sites. Float-collecting spots might have a few battered rocks, a limited number of pits, and loose copper fragments. The big bedrock mines have that layered look of repeated investment. Pits reopened, expanded, abandoned, and then cut into again nearby. Trenches chasing veins that pinch out and then reappear. Spoil heaps that build up over generations. The labour implied by this is quietly enormous, especially when you remember that it wasn't done by huge centralised work crews with overseers and time cards. It was done as repeated small acts, returned to year after year. A family group might come back to the same outcrop each season, widening a pit a little, following green-stained cracks deeper, testing new spots along the ridge. Over centuries, that pattern produces landscapes that feel strangely worked, even though no single episode was grand in scale. The magnitude lives in the accumulation. The toolkit they used for this work was simple on paper, sophisticated in practice. Hammerstones did the brute work, pounding to fracture rock, to break off copper masses, to spoil away the more brittle host material. Wooden levers, thick branches or shaped timbers could be wedged into cracks and used to pry slabs loose, taking advantage of natural bedding planes and frost fractures. The combination of impact and leverage let people move material that would be impossible to budge by hand alone. There's also the question of fire setting. Fire setting is an ancient technique where you build a hot fire directly against rock, let the heat soak in, and then quench it rapidly with water. The thermal shock can crack the stone, making it easier to break with hammerstones and levers. In the Lake Superior region, there are places where charred wood and reddened, heat-altered rock occur in mining contexts, and some 19th-century observers described burned rock and charcoal in old pits. That fits with fire setting as a likely tool in the kit, though in many locations the evidence is faint or has been disturbed. What all of this looked like in the moment was probably less like an industrial operation and more like heavy, seasonal craft. A few people at a time, perhaps, rotating between mining, hunting, fishing and everything else life required, slowly teasing copper out of the earth. The challenge, from our vantage point, is that these signatures have had thousands of years to blur. Rain and snowmelt soften the edges of pits and trenches, slumping their sides in. Frost heaves shift stones around, trees take root in spoil piles, their growth and eventual fall churning the soil. Beavers flood low areas, streams reroute, lakes rise and fall. In some places later indigenous use left another layer of features. In others, 19th and 20th century industrial mining blasted straight through the old workings, sometimes scraping away or remining the very spots that had been laboriously opened in the archaic period. By the time archaeologists arrive with notebooks and GPS units, they're often reading a palimpsest. A pit might be partly filled, its edges blurred into the forest floor. A trench might be cut by a logging road, its spoil piles mixed with modern gravel. Hammerstones might have been moved, collected, or even mistaken for curios and hauled away a century ago. This is one reason the mines can seem underwhelming to visitors expecting dramatic scenes. The evidence is there, but it's subtle, and interpreting it requires piecing together patterns rather than pointing to a single, overwhelming feature and saying, "Look, here it is." And yet, when you stand in one of those quiet clearings, with shallow depressions underfoot and low mounds around you, and you start tracing how they follow the copper-bearing rock, you can feel the scale behind the subtlety. Every hollow is a decision. Every pile of broken stone is a record of blows struck, levers wedged, fires tended. Taken together across the Keweenaw Peninsula, Isle Royale and the mainland shores, these small scars add up to something vast. To see how archaeologists turn these scars into timelines, we have to look at how they actually date the mining itself, often without a single piece of wood or bone in sight. Copper doesn't help us with the calendar. It's a beautiful metal, wonderfully cooperative in the hands, but scientifically, it's almost mute about time. You can't look at a nugget of native copper and run a test that says, this was mined in 1800 BCE. Copper has no built-in radioactive clock the way organic material does. Once it's out of the ground, it just sits there, slowly oxidizing, but not in any way that gives a reliable date. So when archaeologists ask, when was this mine worked, they have to look sideways at the things people left behind that do tell time. Radiocarbon dating is the main tool, and it works on carbon-based life. Wood, bone, plant fibres, anything that was once alive and is now preserved enough to hold a trace of radioactive carbon, that means copper itself is off the table. But the mining process creates situations where organic material can get trapped and sealed. Think about fire setting again. If you're building repeated hot fires against the rock, you're burning wood. Some of that wood ends up as charcoal. If, after a mining episode, the pit starts to fill in with rock chips and soil, that charcoal can get buried and protected. Thousands of years later, an archaeologist trowels down through that fill and finds a little lens of blackened wood. That's datable. Same with tools. We don't usually find complete wooden levers from archaic mines. Wood rots fast in most environments. But once in a while, a fragment of a wooden handle, a bit of sapling wedged into a crack, or fibre bindings from a hafted tool end up in a context that stays damp and low oxygen. In those lucky cases, you can sample those fragments and send them to the lab. Even when the tools themselves are gone, the spaces around them can help. A mining pit might fill in slowly with washed-in sediment. A nearby living area might build up layers of soil rich in ash, discarded bones, broken tools. If you can link those layers closely to the mining, if you can say with confidence, This hearth was used by the people who were working these pits. Then the radiocarbon date on a charred bone or a scrap of wood from that hearth gives you a bracket for mining activity. The problem is that sites don't stay nicely layered. Over thousands of years, pits fill, empty, get reopened, get disturbed by roots, burrowing animals, later visitors, modern collectors, industrial miners. A single old pit can be like a layer cake that's been poked, stirred, and sliced from different directions. That's where the risk of mixing comes in. Imagine a mining pit first dug around 3000 BCE. The miners burn wood, leave hammerstones, maybe a broken antler tine used as a pick. The pit partially fills in. Centuries later, another group comes along, sees the old depression and reuses it. They dig deeper, throw their fresh rubble on top of what's already there, leave their own charcoal and tools. Then, much later again, someone in the 19th century digs a bit, tosses in a broken glass bottle, and walks away. If an archaeologist today takes a single radiocarbon sample from near the top of that fill, without careful stratigraphic control, they might be dating only the last episode of use. Or worse, something that washed in after the mining stopped. A piece of root that died 500 years ago could look like evidence of recent mining if it's not clearly separated from the older mining layers. So the work becomes painstaking. Excavation is slow, layer by layer, watching how the sediments change, mapping where each fragment of charcoal appears, looking for clear boundaries. Here is an old pit bottom. Here is a later cut into it. Here is natural soil washing in after human activity ceased. Even with all that care, some mines yield almost nothing organic. Hammerstones are stone. Copper is metal. Spoil piles are broken rock. In well-drained upland sites, any wood that once lay there is long gone. Fire setting might have been used, but the charcoal could have been trampled, scattered, eroded away, or oxidized to nothing. In those cases, archaeologists can identify the mines, can estimate the labour, can map the extent, yet have little or nothing that can go into a radiocarbon vial. When that happens, the dates get fuzzy. You might have one or two bits of charcoal from a single feature, giving you a couple of points in time that could reflect a brief episode of mining, a campfire years later, or even a lightning strike forest fire that dumped ash into an already abandoned pit. You might have a site where the only datable material comes from nearby camps clearly associated with copper working, but it's not obvious whether those represent the very beginning of mining there, its busy heyday, or a late dwindling phase. This is where archaeologists make an important distinction that doesn't always make it into popular summaries. The difference between the earliest possible use of a mine and its main period of activity. The earliest use is, in theory, the very first time someone pried copper from that spot. In practice, what we usually have is the earliest datable material securely associated with mining. That's not the same thing. If the first generations of miners left no preserved charcoal, their activity will be invisible to radiocarbon. The earliest date we see is actually just earliest preserved date. The main period of activity is about intensity. When were people coming back over and over in numbers big enough to leave a deep footprint? That might be bracketed by clusters of dates, by thick layers of mining debris, by dense concentrations of hammerstones and copper offcuts that all seem to fall within a certain window of time. At Lake Superior, radiocarbon dates from different mining localities scatter across millennia. Some point to use beginning in the late Archaic period, others show extended activity, and still others suggest that certain zones were only briefly exploited. But every one of those dates carries uncertainty, lab error, calibration curves, the possibility that the charcoal came from old wood recycled into a later fire, or from a hearth a little removed from the actual digging. When people say the mines were worked from about this date to about that date, they're really talking about a patchwork of these imperfect signals, stitched together with geological context and careful reasoning. The story of timing emerges not from a single clean timestamp, but from a noisy chorus of little carbon clocks, each ticking down from some long-vanished fire. Once you understand that, the scale of the mystery changes. The question isn't just, how old are the mines? It becomes, how much work fits into those broad windows of time? To answer that, we have to step back from single pits and look at the whole landscape. So let's zoom out and ask the question that pulled so many people into this story in the first place. How big was it really? If you've poked around books, documentaries, or certain corners of the internet, you've probably seen some striking numbers. Claims that ancient miners around Lake Superior removed 500,000 tons of copper, or 1 million tons, or that there were 10,000 ancient mine workings, all labouring away for mysterious purposes. These big round figures circulate because they're satisfying. They turn a messy archaeological landscape into something that sounds precise and dramatic. 500,000 tons feels like a number you can picture. It suggests armies of workers, vast projects, maybe even lost civilizations. The reality is both quieter and more interesting. Those large totals don't come from some hidden archive of ancient mining records. They come from modern people looking at pits, spoil heaps and geology, then making a chain of assumptions. Imagine standing on one of the old mining ridges. You see a depression in the bedrock, maybe a few meters across, partly filled with rubble. Around it is a low ring of broken rock, the spoil. If you could magically rewind time and watch the miners work, you'd see the pit deepen, the spoil pile grow, and the best copper pieces carried away. Since we can't rewind, we work backwards. The first step is volume. Surveyors can measure how big the pit is today, length, width, depth. They can map how much spoil is still piled around it. In some cases, 19th-century mining engineers did exactly that, recording dimensions of ancient works before blasting them away in the industrial rush. From those measurements, you estimate how much rock was moved. A simple way is to treat the pit like a geometric shape, a rough cylinder or a cone or a sort of bowl. Length times width times an average depth gives a crude volume. Combine that with estimates for how much broken rock the spoil pile once contained, and you get a ballpark figure for the total rock removed at that location. Then comes the leap from rock to copper. Not every bit of rock in a native copper deposit carries the same load of metal. Some zones are rich, thick veins, heavy masses, chunks that practically glow green with oxidation today. Others are lean, scattered stringers, tiny blebs in the basalt, lots of effort for very little reward. When people try to turn pit volume into tonnage of copper, they have to pick an average copper content for the rock. Maybe they say, let's assume this ore ran 1% copper, or 2%, or 0.5%. They might base that on modern geological studies, or on what was typical for similar deposits, or in less careful cases, on not much at all. Multiply the total rock volume by that percentage, apply a density, and suddenly you have a number of tons of copper that could have been present. Then there's another step. How much of that copper did ancient miners actually remove? Prehistoric mining wasn't strip mining. People weren't grinding every bit of rock to powder to extract every atom of copper. They were hunting the obvious accessible pieces, nodules, veins thick enough to pry out, plates that could be pried away with stone and fire. So whoever is doing the estimating has to decide what fraction of that theoretical copper did people take. Half, a quarter, more, less. That choice can easily double or halve the final number. Now scale up. Do this for one pit, then another, then a whole ridge. Then, if you're feeling bold, extrapolate from the surveyed area to all the similar unsurveyed ridges you think might have been worked. Soon you're generating regional totals, tens of thousands of cubic meters of rock, hundreds of thousands of tons of copper removed. You can see how, at each stage, a small change in an assumption ripples outward. Assume thicker deposits, and the tonnage swells. Assume thinner, and it shrinks. Assume that most of the original spoil is still there, and your volume estimates stay high. Notice that much of it eroded away downslope over millennia, and you realize your visible piles may be only a remnant. Use careful modern geological data, and you might revise older, more optimistic numbers downward or upward. On top of that, we don't even have a complete inventory of all prehistoric mining features. Some old pits were obliterated by 19th and 20th century industrial mining. Others are hidden under forest, soil, or development. Early counts of ancient mines sometimes treated every depression as a separate working, even when later mapping showed that many were connected parts of one larger system. In other cases, shallow test holes may have been labelled as mines, when they were really just exploratory scrapes. So we're working with incomplete surveys, eroded landscapes, and variable geology. It's like trying to estimate how many books were once in a library by looking at a few surviving shelves, some scattered pages, and the outlines of where other shelves might have stood. That's why there's such a gap between two statements that sound similar on the surface. There is a lot of evidence for extensive prehistoric copper mining around Lake Superior, and ancient people removed exactly 600,000 tons of copper from these mines. The first is well supported. Across Isle Royale, the Keweenaw and neighbouring regions, we see hundreds, probably thousands of mining features: pits, adits, trenches, hammerstones, fire-setting scars. The labour involved, spread over centuries and millennia, was unquestionably substantial. The second statement, the precise tonnage, is where the ground gets soft. Those bold numbers depend on stacked assumptions about how representative surveyed areas are, about how rich the deposits were, about how intensively people exploited them, about how much spoil has been lost. Reasonable scholars, using the same basic evidence, can come up with very different totals. Some archaeologists and geologists are comfortable saying the amount of copper removed was large, certainly in the thousands of tons, possibly tens of thousands. Others are more cautious, emphasizing the uncertainties and urging us not to turn back-of-the-envelope calculations into facts carved in stone. What almost everyone agrees on is this: prehistoric mining at Lake Superior was real, long-lasting and significant in human terms. Small groups of people with stone hammers and fire removed an impressive amount of native copper over many generations. They left a landscape pocked with pits and ringed with spoil. They altered ridges, created work sites, and moved raw metal into broader trade networks. What remains debated is the exact scale in modern industrial units. Was it closer to what a single 19th-century mine might produce in a few busy years? Or was it more modest than the biggest modern numbers claim? Those big figures make for dramatic headlines and fuel stories about vanished empires and lost fleets of copper-laden ships. But if we treat them as tentative, as estimates, not as revealed truth, the picture that remains is no less intriguing. Because even without settling on a final number, we're left with a landscape of deep time labour. Thousands of years of people returning to the same rock faces, teaching their children where to strike, how to build the fires, how to carry the heavy green-tinged metal away. And that raises the next question, the one that turns all those pits into a mystery. If so much copper really did leave these ridges, where did it all go? If you start with the highest estimates of copper taken from these mines, the next step almost feels automatic. You look around at the archaeological record and ask, where is it? If 500,000 tons of metal really left these ridges, shouldn't we be drowning in copper tools? Shouldn't there be museum cases overflowing with Lake Superior axes and spear points? Shouldn't every burial mound from the Great Lakes to the Gulf Coast have glittering copper plates stacked like poker chips? That intuitive expectation is what fuels a lot of missing copper stories. The math seems simple. Huge production should mean huge artifact counts. When the artifact counts look modest by comparison, it feels like something must be wrong. Either the estimates are wildly inflated, or the artifacts went somewhere we haven't accounted for. Probably both are true, but not in the dramatic civilization-sinking way people often imagine. First, it helps to remember that we're thinking in two different currencies. Modern conversation uses industrial numbers, tons, production curves, output per year. Ancient life ran on individual objects, an adze, a chisel, a rolled bead, a small awl for piercing leather, a single copper knife that might be sharpened, resharpened, and handed down across generations. Even if we conservatively imagine thousands of tons of copper extracted over millennia, that doesn't translate into a mountain of separate artifacts. Copper is dense. A single bar the size of your forearm can weigh several kilos. A single heavy ingot can be hammered into dozens of small tools, then rehammered, reforged and recycled many times over. That's the next piece. Loss pathways. Copper, unlike stone, is soft and workable. That's the whole point of using it. If the edge of a stone axe chips, you nap a new one. If a copper axe bends or dulls, you can anneal it in the fire, hammer it back into shape, or cut it apart and turn it into something else. Every time that happens, the original artifact disappears from the archaeological count. Over a few hundred years, a community might take the same pool of copper and run it through dozens of forms. Tools, ornaments, trade pieces, ritual items. When a piece broke, the metal wasn't thrown away. It was opportunity. Recycle became the default. Later, when other metal technologies arrived in the region, bronze elsewhere, iron much later in North America, that pattern continued. Old copper objects became convenient raw material. You didn't need to trek back to a ridge on Isle Royale. You could melt down your grandmother's armband. So when archaeologists dig, what they're seeing is not how much copper was ever used here. They're seeing how much copper escaped generations of reworking, reuse and loss. Some copper did leave circulation in more final ways. Burial practices occasionally took metal out of everyday life. But even here, the picture is complicated. Some graves were rich, others had only a single bead or none at all, and many burial grounds have not survived intact. Ploughed fields, construction, river erosion, and simple chance mean that only a fraction of ancient cemeteries have ever been identified, much less excavated. Looting adds another layer. For at least a few centuries, people have sought ancient copper the same way some seek old coins or arrowheads. Mounds were opened, pits were dug, artifacts were scattered into private collections or sold without records. Each time that happened, context was stripped away. A copper spear point in a desk drawer tells you almost nothing about where it came from, what it was buried with, or how it fit into a trading world. And then there's the slow decay that comes from simply being buried in a wet, acidic environment for thousands of years. Copper does survive better than many materials, but it's not immortal. It corrodes, delaminates, flakes away. Thin sheets and finely worked ornaments are especially vulnerable. By the time a backhoe or an archaeologist's trowel reaches them, some have already crumbled beyond recognition. So yes, copper survives. But the stories attached to it, who used it, how, where it travelled, often do not. That's where preservation bias comes in. Archaeology isn't a census. It's a sampling process heavily filtered by geology, land use, and pure luck. Sites on high, sandy ground have a different survival rate than sites on low, flood-prone terraces. Places that became towns and cities have been churned and built over. Places that stayed remote might still hold intact deposits of artifacts no one has ever seen. Museums, in turn, are not neutral mirrors of the past. They reflect what was collected, when and by whom. In the 19th and early 20th centuries, big, showy pieces were prized. Smaller, plainer tools might be overlooked, miscatalogued, or left in private hands. A display case full of elaborate copper ornaments doesn't tell you how many modest workaday tools were out there. It tells you which items collectors found most interesting. So when someone says, "We mined X tons, but only Y artifacts sit in museums," the rest must be missing. They're conflating two different things. Missing from museums is not the same as missing from history. Most copper that was ever mined at Lake Superior probably did exactly what you'd expect useful material to do. It cycled through generations of tools and ornaments. It travelled hand to hand along trade routes. It was buried with some people, abandoned in old camps, lost during moves, dropped in rivers, sacrificed in rituals, reworked when needs changed. Each of those steps took it one notch further away from the sort of neat, documented objects that end up with accession numbers and climate-controlled storage. And that brings us to an important point for the rest of the story. Trade, especially in a world without writing, can be archaeologically quiet. It can move through perishable containers, over water, across seasonal campsites that leave only faint traces. It can spread a useful material thinly across vast regions, so that no single site is spectacularly rich in copper, even if the underlying network is extensive. In other words, the puzzle isn't just, where did the copper go? It's also, what kind of record would we expect it to leave if it moved mostly through subtle, everyday channels? To answer that, we have to follow the metal outward from the mines and into those quiet networks, where goods, stories, and people travelled together, and where the archaeological footprints can be surprisingly hard to see. If you stand on a modern highway overpass, you can see movement. Cars stream by. Signs tell you where they're headed. GPS logs every turn. Ancient trade wasn't like that. It didn't leave concrete mile markers and customs posts. It moved more like groundwater. Slow, quiet, seeping through the same landscape generation after generation until distant places were linked in ways no single person ever fully saw. Around Lake Superior, the main arteries weren't roads at all. They were water. The Great Lakes are an inland ocean system stitched together with rivers, portages, and short overland carries. For indigenous peoples long before Europeans arrived, this was a travel web. Birch-bark canoes could carry people, dogs, tools, children, and yes, heavy materials like stone and copper, with a fraction of the effort it would take to drag them over land. Picture family groups moving seasonally to follow fish runs and wild rice harvests, bands meeting at good fishing spots or maple sugaring camps, marriages arranged, news exchanged, small gifts offered, and sometimes copper changing hands. A socketed spear point traded for furs, a set of copper awls exchanged for high-quality chert from far away, a roll of raw copper passed along to a skilled worker in another village. From there, the pattern scales outward. Archaeologists talk about down-the-line exchange. It's exactly what it sounds like. A group living near a source of a valued material doesn't ship it directly to some far-off region in bulk, like a modern export company. Instead, they trade a little with their neighbours. Those neighbours trade a portion of what they've received with their neighbours, and so on. Each step moves the material farther, but it also thins it out. By the time a piece of Lake Superior copper reaches, say, a river valley in what's now Illinois, it may be just one or two objects in a whole community's toolkit. Not a warehouse, not a hoard, just a knife, a bead, a small axe head with its own quiet journey behind it. So how do we even know such networks existed? Trade doesn't come with receipts, but it does leave a few consistent fingerprints. One is sourcing. Certain rock types, shell species, or metals are geologically distinctive. Obsidian from one volcano has a different trace element signature than obsidian from another. Marine shells from the Gulf Coast don't naturally appear 1,000 kilometres inland. Native copper from Lake Superior has its own isotopic flavour. When objects made of those materials are found far from their natural sources, they point to movement. Not necessarily a single spectacular expedition, but connections, people handing things on. Another fingerprint is typology. When similar styles of artifacts show up over a broad area, especially if the style is specific and clearly not the local default, it suggests ideas or goods are moving. A particular way of shaping a copper spear point. A characteristic way of rolling a tube bead. If you see the same style turning up again and again across hundreds of miles, it hints at shared traditions and by implication, shared networks. Then there are find spot patterns. Copper artifacts in one region might cluster along certain river systems, or appear mostly in burial mounds of a particular era. If you map those occurrences, you start seeing corridors, chains of sites that mark favoured travel routes and old alliances, even when there's no obvious road. But all of these clues are partial. They skew toward the durable and the distinctive. Most of the infrastructure that carried trade in the ancient Great Lakes world was perishable. Birch bark canoes rot. Cordage unravels. Leather straps, woven bags, wooden paddles, bark baskets. These are the things that would have held copper tools, traded food, pigments, ritual items. In a wet climate over a few thousand years, almost all of that vanishes. You're left with the rare surviving copper piece, sitting in the soil like a period at the end of a sentence that's otherwise been erased. Even the copper itself doesn't have to travel in obvious shapes. It can move as finished objects. A polished knife, a pendant hammered thin and decorated. But it can also move as blanks, roughly shaped pieces ready to be finished by the buyer, or as unworked chunks and ingots. A family a week's paddle from the mines might specialize in turning raw copper into standardized bars, easy to stack in a canoe, easy to weigh in the hand. Every time the form changes, some information is lost. If archaeologists find an ingot far from Lake Superior, is there evidence of direct contact with mining communities? Or did that bar pass through 6 different hands, melted, reshaped, and repurposed along the way? If they find a simple awl, does its plainness mean it was made locally from local copper, or made hundreds of miles away from imported metal that's chemically indistinguishable from a closer source? Sourcing helps, but only up to a point. Typology helps, but people copy styles. Find spot patterns help, but the sample size is tiny compared to everything that's been lost. And then there's the subtle arithmetic of down-the-line exchange. Each community takes a cut. A village might receive 10 copper pieces from its northern neighbours and send 6 southward. The rest get folded into local life. Children inherit them. Tools wear out and are reforged. A piece goes into a burial. Another is cached and never recovered. A few are lost on a portage trail and sink into the mud. Multiply that thin, steady trickle by centuries, and trade can move enormous amounts of material without ever producing the kind of dense, spectacular caches that would leap out in the archaeological record. From a modern perspective, it's tempting to look for corridors of overwhelming evidence, a line of sites so rich in copper that you can trace an arrow on a map and say, there, that's the route. But that expectation comes from our experience of highways, railroads, and ports, and ancient exchange was more like a many-threaded web, flexible, seasonal, constantly renegotiated. Some threads were strong, linking the mining districts to nearby shores. Others were faint, passing a few objects a generation across cultural boundaries we barely understand. The key point is simple and easy to miss. The absence of a clear, bold copper highway on our maps doesn't mean the copper sat still. It means the movement happened through systems that don't fossilize well. Water routes instead of pavement, kinship obligations instead of contracts, bark canoes instead of barges, everyday tools instead of treasure chests. The metal could have moved widely, yet left only scattered echoes, isolated artifacts, faint chemical signatures, stylistic hints in a handful of graves and village sites. When we remember that, the supposed mystery of no trade routes starts to look less like a smoking gun and more like a mismatch between what we're able to see and how ancient people actually lived. To push further, we have to look even closer at those scattered echoes, at the chemistry locked in the copper itself, and at how far that can and cannot take us. When people hear that copper has a signature, it's easy to picture something like a barcode. Scan it and a machine tells you Lake Superior, 3000 BCE, shipped on canoe number 12. The reality is more like tasting a soup and trying to guess the recipe. Copper is never perfectly pure in nature. Tiny amounts of other elements get mixed in when it forms. Silver, arsenic, antimony, bismuth, a little of this, a trace of that. The exact recipe depends on the rocks, the fluids, the temperature and pressure deep underground. It also depends on the particular deposit. Even within one mining district, different veins can have slightly different flavours. On top of that, you have isotopes. Lead isotopes are especially useful. Lead has multiple stable forms, same element, different atomic weights. How much of each form ends up in an ore body depends on the long, slow radioactive decay of uranium and thorium in the rocks around it. Different geological histories, different isotopic ratios. So when a scientist takes a tiny shaving from an ancient copper artifact, dissolves it in acid, and runs it through a mass spectrometer, they're looking at two things at once: the trace element spice mix, and the isotopic accent, especially of lead, but sometimes of other elements too. If that combination matches known samples from a particular region, say the Keweenaw Peninsula on the south shore of Lake Superior, that artifact becomes a candidate for having come from there. Not a certainty, a candidate. This is where the story often gets bent out of shape. On one side, you'll hear claims that science has proved huge amounts of old world metal came from Lake Superior. On the other, you'll see blanket dismissals that you can't trace copper at all, it's impossible. Both reactions skip over the careful, slightly uncomfortable middle ground where the actual data live. The strengths are real, some ore bodies are distinctive. Their trace element profiles don't look like most others. Their lead isotopes fall into tight, unusual clusters. When you analyse enough geological samples from enough regions, you can sometimes say with reasonable confidence, this artifact almost certainly came from this general district, and probably not from those others. That's how archaeologists have traced obsidian from specific volcanoes into prehistoric trade networks. It's how they've linked Bronze Age tin ingots to particular mining fields. This same logic applies to copper, at least in principle. When we turn that logic on the Great Lakes, a few things stand out. Artifacts from the immediate Lake Superior region, places like northern Wisconsin, Michigan's Upper Peninsula, and parts of Ontario, often match native copper deposits in that area quite well. The chemistry says, yes, this is local metal, worked close to its geological home. As you move farther away, the picture gets fuzzier, but there are still promising matches. Some copper artifacts in the broader Midwest and eastern woodlands show trace element and isotopic signatures that are consistent with Great Lake sources, not identical to every sampled vein, but falling within the same broad family. Put together with typology and find spot patterns, this builds a solid, if partial, case that Lake Superior copper travelled hundreds of miles through Indigenous trade networks, not just as a rumour, but as a real material, in real hands. That's the secure part. Lake Superior copper fed into a regional exchange system. Some of the metal found outside the immediate mining districts almost certainly started its life in those old pits and bedrock exposures along the shore. Where the ground gets slippery is when people try to extend that picture across an ocean. Bronze Age artefacts from Europe and the Near East have been analysed too. Some of them do show chemical and isotopic profiles that overlap with ranges seen in North American native copper. Overlap here is the dangerous word. Geology is messy. There isn't a unique Lake Superior ratio that no other region on Earth shares. There are clusters, patterns, tendencies. Some European copper ore bodies have trace element and lead isotope combinations that land in similar parts of the graph as some Great Lakes samples. Others don't. Many lie somewhere in between. Now add sampling. We don't have a perfectly complete catalogue of every copper deposit on Earth, measured to high precision. We have patchwork. Some regions are well characterised with dozens or hundreds of samples. Others have barely been touched. Within a single mining district, one sampled vein might look distinctive, while another, 10 metres away and never measured, could skew the whole picture if we knew about it. So when a Bronze Age artefact lands in a zone that overlaps the Great Lakes range, that can mean several different things. It might genuinely match Lake Superior copper. It might match some unsampled or undersampled deposit in Europe or Asia that happens to share a similar isotopic accent and trace element flavour. It might be a mix, metal recycled and alloyed from multiple sources, averaging their signatures into something ambiguous. Recycling is its own problem. Once people start melting and blending metals, you lose the clean, single deposit fingerprint. It's like pouring wines from 3 vineyards into one barrel, and then trying to say which specific hillside the final drink came from. This is why most specialists are cautious. They'll phrase things in terms of probabilities and compatibilities. Consistent with, cannot rule out, unlikely given current comparative data. They draw error bars. They note how many geological samples they're basing their comparisons on. They warn that new data could shift the picture. Popular maps often don't. You've probably seen them. Bold arrows curving from Lake Superior to the Mediterranean, captions declaring that trace chemistry proves a transatlantic copper pipeline. If you try to track those arrows back to their sources, you usually find a handful of overlapping data points, interpreted as if overlap equals identity. A cluster on a graph becomes a straight line on a world map. A statistical could be quietly hardens into is. That's not how good science works, and it's not how the scientists who actually do these measurements talk about their results. When you look closely at the technical literature, a calmer picture emerges. Sourcing studies strongly support the idea that Great Lakes copper was important within North America. They give us a way to sort out local versus imported metal at regional scales. They help us see the outlines of trade webs that pottery shards and burial sites only hint at. When it comes to old world artifacts, the same methods raise interesting questions, but they don't close the case. Some objects have signatures that are intriguing, hard to match cleanly to known Eurasian sources. Others fit local ore fields just fine. Still others sit in the grey zone where multiple geological histories could produce similar numbers. Instead of a solved mystery, we get a refined one. We can say, with more precision than a century ago, where some copper definitely didn't come from. We can sketch zones of higher and lower likelihood. We can rule out simple, dramatic stories that ignore the complexity of the data. What we can't do, at least not yet, is draw a single confident arrow from Lake Superior to Bronze Age Europe and say, there, that's the missing 500,000 tons. The chemistry sharpens our questions. It trims away some fantasies and forces others to be more careful. It shows that the mines around Lake Superior were plugged into real networks of movement and exchange. But it also underlines how much we still don't know about the full life histories of all that metal. To see why, and to really judge the scale of the puzzle, we have to step back and look at what was happening with copper and bronze elsewhere in the world at the same time. When people zoom out from Lake Superior to the whole old world, the The comparison that grabs attention is the Bronze Age. From about 3300 BCE onward in the Near East, and a bit later in Europe, copper use ramps up dramatically. You start seeing metal in tools, weapons, ornaments, fittings for chariots and ships. Palaces and temples are taking inventory of metal the way later states will count coinage. In some regions, copper and bronze become the backbone of elite power. If you do a back-of-the-envelope estimate of all the copper that went into Bronze Age artifacts, building fittings, lost or recycled goods, and industrial waste across the Old World, you end up with very big numbers. Not precise numbers, but clearly in the hundreds of thousands of tons over many centuries. Lay that mental pile of metal next to the rough estimates for how much copper might have been removed from the Lake Superior mines, and the temptation is obvious. Two large quantities, one apparent surplus, one insatiable demand. Draw a line, solve the mystery. But the Bronze Age doesn't just run on copper, it runs on bronze. And bronze is picky. To make true tin bronze, the classic mix that gives you harder, more durable metal than pure copper, you need tin. Not a lot in percentage terms, but enough that someone has to go out and find it, mine it, and move it. Tin is much rarer in accessible form than copper. Usable tin deposits are scattered. Parts of Central Asia, Anatolia, Iran, later Cornwall and Iberia, a few other pockets. For Bronze Age metallurgists, tin was the bottleneck. You can see this in the archaeology. There are long stretches where people are making arsenical bronze, basically copper, accidentally or deliberately contaminated with arsenic from certain ores. It behaves little better than pure copper, but not as nicely as tin bronze, and it can be toxic to work with. When true tin shows up in the record, it's a game changer, and the routes that carry it, overland caravans, riverine trade, coastal shipping, become extremely valuable. So even if you imagine a secret river of Lake Superior copper pouring into the Old World, it wouldn't automatically solve the Bronze Age's real constraint. Without reliable tin, you don't get the full technological and military advantages that define the period. You just get more copper. Useful, yes. Transformative, only up to a point. Alloying practices complicate the picture further. Old World smiths weren't just tossing any metal into a crucible. They were learning, generation by generation, how different mixes behaved. A little more tin for a sharper blade, a little less for a tougher axe, occasionally a dash of lead for better casting. By the Middle and Late Bronze Age, many regions had developed fairly standardized recipes, tuned to local tastes and ore supplies. Those recipes leave clues. If a large volume of foreign copper suddenly entered the system, especially from an unusual geological background, you'd expect to see more than just a few curious isotopic overlaps. You might see shifts in impurity patterns across many objects, changes in slag chemistry at smelting sites, new routes in the distribution of ingots. In principle, you could even catch hints of it in textual sources once writing appears. References to new suppliers, strange lands, or sudden surpluses. That doesn't mean such evidence would be glaringly obvious. Bronze Age trade networks were already complex. Copper was moving from Cyprus, Anatolia, the Balkans, the Alps, Central Europe, the Caucasus. Tin was coming from its own scattered nodes. Metal was being melted, mixed, recycled, and redistributed over and over. But when we add an ocean to that picture, the hurdles go up sharply. Moving bulk copper across the Atlantic in pre-Iron Age conditions is not like tucking a few beads into someone's luggage. Copper is heavy. Ingots or raw chunks add up fast. To supply a meaningful fraction of Old World demand, you'd need regular traffic. Fleets of seaworthy vessels making long voyages on at least a semi-predictable schedule. That implies shipbuilding traditions capable of open ocean travel, navigation methods stable enough to hit roughly the same coasts repeatedly, and coastal infrastructures on both sides that can handle receiving and redistributing the metal. You'd also expect cultural traces to accumulate around those movements. Even if the trade itself were restricted to a small elite, the physical footprint would be hard to keep invisible over centuries. Harbour works, wrecks, foreign goods showing up out of place in burials and hoards, myths and origin stories that look suspiciously like distant memories of crossing a great western sea. So far, the hard evidence for that kind of structured transatlantic metal trade in the Bronze Age just isn't there. What we have instead is a debated hypothesis. Some researchers look at the combination of large estimated mine volumes in the Great Lakes, mysterious shortfalls in identified Old World copper sources, and those few intriguing chemical overlaps, and they say, maybe there was some limited long-distance contact. Maybe a trickle of New World copper made it into Old World networks, leaving just enough of a chemical echo to tease us. Others point to the well-documented Eurasian mining districts, places like Cyprus, the Timna Valley, Bulgaria's massive copper deposits, the Alpine mines, and argue that we haven't exhausted the Old World possibilities yet. There are known fields that haven't been fully quantified, and probably unknown ones as well. They see no need to invoke an Atlantic bridge when local explanations can, in principle, fill the gap. Most specialists sit in a cautious middle. They'll say that long-distance seafaring was certainly within human capabilities by the later Bronze Age. They'll note that small-scale contacts across wide stretches of ocean are not impossible in deep time, but they'll also insist that extraordinary claims about large-scale resource pipelines need extraordinary multi-line evidence, not just chemistry at the edge of its resolving power, but archaeological contexts, ship remains, settlement patterns, and clear discontinuities in existing trade systems. Until that constellation appears, the Bronze Age drained Lake Superior remains a provocative idea, not a demonstrated reality. There are quieter alternatives that don't require transoceanic contact. One is that the estimates for Great Lakes production are too high. They're based on visible excavation volume and rough assumptions about how efficiently ancient miners used their tools. If those assumptions are off, the supposed surplus shrinks. Another is that a lot of that copper never left North America in dramatic form. It may have been worked, reworked, lost, buried, corroded, recycled, and eroded away over thousands of years within indigenous societies, whose material traces were partly destroyed by time and later disruption. A third is that the Old World's missing copper is still sitting in unrecognized or unexcavated mines, or in slag heaps and low-grade ores no one has bothered to quantify. Archaeology is always skewed toward what we've happened to find. None of these explanations are entirely satisfying. Each leaves some loose threads, but they remind us that we don't have to leap straight from big mines and big demand to a single sweeping conclusion. Between those two are many smaller, messier stories, regional trade webs, technological choices, errors in our own reconstructions. To see how those might play out closer to home, and how our modern fascination with lost cargoes and secret voyages took shape, we have to jump forward in time to the century when people first stumbled into those ancient pits with industrial eyes and Victorian imaginations. When industrial prospectors arrived at Lake Superior in the 19th century, they thought they were coming to open a new chapter. They didn't expect to find out they were walking into the middle of a very old one. Imagine you're a miner in the 1840s, cutting your way through forest toward an outcrop you've heard has native copper sticking right out of the rock. You crest a ridge, push through brush, and there it is. Not a pristine vein, but a shallow depression already dug into the basalt, trees growing in it, the walls softened by time, and on the bottom, when you clear away the roots and soil, you hit old hammerstones, fire-cracked rock, maybe a rotten timber or a broken wooden shovel, darkened and fragile. You came expecting untouched ground. What you find looks like someone else has been here not just recently, but long enough ago that the forest has had time to recover and forget. This kind of encounter happens again and again. Surveyors map lines and keep tripping over irregular pits marching in rows along the ridges. Company men sink test shafts and pull up stone walls with telltale bruising from repeated blows. An engineer writes back to his boss that an ancient race of miners seems to have stripped the best of the loads and left only the deeper, harder ore. To people steeped in the sensibilities of the 1800s, this isn't just an interesting detail. It's a story seed. Newspapers are hungry for copy. Investors need reasons to believe that their particular patch of ground is the one worth backing. Local boosters are trying to transform remote shorelines into the next big mining district. When they hear about ancient pits and old workings, they recognize the hook immediately. Reports start to appear in regional papers and mining circulars. A prospector describes a pit 60 feet long, with tons of rubble that must have been removed by unknown hands. A visiting clergyman writes about hundreds of such pits scattered for miles. A company agent claims to have found a single mass of copper weighing several tons, evidently exposed by the ancients. Sometimes these early observers are cautious. They hedge their numbers with phrases like, "perhaps," "it is estimated," "said to extend." They admit that they haven't personally measured every depression or weighed every chunk. But those qualifiers don't always make the trip when other people repeat the story. By the time a second or third writer gets hold of the same observations, hundreds of pits can become thousands, covering the country as far as the eye can see. A mass of copper weighing several tons is rounded up to 10 tons, then 20. Phrases like, "it is believed that" quietly slide into "it is known that." Conjectures harden into pseudo-facts simply by being stated enough times in confident tones. This is how numbers start to accumulate. One surveyor estimates that a particular hill might have yielded a few thousand tons of copper if fully worked. A decade later, a popular article quotes, "thousands of tons removed by an ancient people." Another writer, eager to impress, strings several such claims together and concludes that not less than 500,000 tons must have been taken from the region as a whole. Nobody in that chain has actually weighed 500,000 tons of anything. They're extrapolating from impressions, from partial measurements, from what they think the landscape suggests, but each repetition makes the figure feel more real, until later readers encounter 500,000 tons as a solid, carved-in stone number, rather than what it originally was, a speculative guess on top of other speculative guesses. To be fair, some 19th-century records are remarkably sober. Geologists and engineers trained in careful observation write detailed descriptions of pit dimensions, tool types, charcoal layers, and tree growth. They distinguish clearly between what they saw and what they inferred. They sketch maps, list measurements, and sometimes express open skepticism about the wilder claims already circulating in the press. Those early technical reports are invaluable today. They capture features that have since eroded, been overgrown, or been destroyed by later mining. They give us a direct look at the ancient workings before a century and a half of industrial disturbance. But those measured voices were sharing the stage with a different style of storytelling. Victorian writers loved mystery. They were fascinated by lost races, vanished civilizations, and dramatic contrast between the supposedly primitive present and an imagined glorious past. When they heard about miles of ancient pits and huge copper masses abandoned in the ground, it slotted neatly into that mental template. Instead of describing indigenous communities as the long-term inhabitants and engineers of the region, many writers framed the old mines as the work of some separate, vanished people. "The race that wrought these mines is gone," one author declares, despite living within reach of Ojibwe communities with oral histories and knowledge of the landscape. This wasn't a neutral mistake. It was tied to ideas about progress, race, and who counted as a legitimate ancestor of civilization. Layer that onto the natural human tendency to round up, simplify and dramatize, and you get a powerful mix. An engineer's careful note about numerous pits from 10 to 20 feet deep becomes a tourist guide's breathless claim that the entire district is honeycombed with deep ancient shafts. A mining report's cautious, may have removed many tons, turns into a newspaper's untold millions in copper carried away in prehistoric times. Fast forward a century and a half, and those Victorian echoes are still with us. When you scroll through modern articles and videos about Lake Superior's missing copper, you'll often see the same numbers, the same phrases, even the same 19th-century quotations, recycled as if they were fresh discoveries. The original context, the guesses, the uncertainties, the promotional motives has usually been stripped away. A speculative 500,000 tons from an 1800s booster pamphlet shows up in a 21st century blog as a firm minimum. A miner's impression of pits as far as the eye can see is treated as a literal survey. A single dramatic case, a big mass of copper, left partly worked in an old pit, is silently multiplied until it seems as though the entire district is full of abandoned megalodes. And because the modern internet loves tight, striking narratives, the most dramatic version tends to win. Ancient indigenous miners develop sophisticated techniques and work these deposits for thousands of years. Is a true and fascinating sentence, but it doesn't travel as fast as 500,000 tons of copper vanished without a trace. Over time, a whole secondary literature grows up, not of new observations, but of repetitions and embellishments. People quote each other, not the ground. The mines themselves become almost secondary to the stories about the mines. Sorting through this tangle requires a slow kind of reading. You have to ask, each time you see a claim, who first said this? What did they actually see? Were they measuring or estimating from a distance? Were they trying to describe or to sell? And then you have to ask a harder question. How much of what we think we know about the Lake Superior copper mystery is based on rock and charcoal and tools, and how much is based on the narrative habits of the 19th century echoing into our feeds? To answer that, we need to peel the layers apart, separate the earliest observational records from the later, more romantic retellings, and see what remains when the legend dust settles. Once you start peeling those layers back, you run into a different kind of problem. It's not just that some of the old numbers are exaggerated, it's that the ground itself doesn't cooperate with clean, satisfying arithmetic. The archaeological record around Lake Superior is a patchwork, not a neat quilt designed by someone with a plan, but a set of scraps rescued from a house that's been remodelled, flooded, burned in spots and then partially bulldozed. We have some sites that were recorded in obsessive detail. An engineer in 1850 sketches every pit on a particular ridge, notes the depth, the tool types, the thickness of charcoal. A 20th century excavation on a single island documents each layer of soil, each copper offcut, each burned log. Then, a few miles away, we have only a line in a report. Numerous old diggings observed along the shore. No map, no measurements, no precise location. And in between those two extremes are the places that were noticed, maybe even visited, but never formally recorded. A prospector's notebook that didn't make it into an archive. A local guide's memory of old pits up there somewhere that was never turned into coordinates. When modern archaeologists try to reconstruct the scale of ancient copperworking, they're not working with a complete data set. They're working with what has survived of older observations plus whatever they can still see on the land today. That means the evidence is inherently uneven. Some ridges were mapped 3 times, others not at all. Some coves were carefully tested with small, controlled excavations. Others were stripped wholesale by industrial mining before anyone had a chance to take notes. And then there's the time and money problem. Archaeology is slow and expensive. It's not just digging, it's permits, community consultations, lab work, radiocarbon dates, specialist analyses, curation. You can't just say, we'll excavate every old copper pit on the Keweenaw and then go do it. Most projects are small, a handful of test units at one promising site, a survey along a new road corridor, a revisit to a famous location to see what's left. Those narrow windows can tell us a lot about technique, about dates, about local organisation, but they don't automatically scale up to region-wide totals. Trying to move from here is what we saw in these 3 pits to here's exactly how many tons were mined over thousands of years is like trying to estimate a forest from one clearing. And the forest itself hasn't stood still. Since the 19th century, modern activity around Lake Superior has done to the ancient record what the ancient record had already done to the ore bodies: remove parts, rearrange others, blur the edges. Industrial mining often targeted the same veins the old miners liked. To sink a modern shaft, engineers cleared the surface, bulldozed old pits, scooped up hammerstones and charcoal and dumped them as overburden. Some of those artifacts were noticed and set aside. Many were not. Logging removed old trees whose growth rings might have given us maximum ages for abandoned workings. Roads and rail beds cut through ridges where pits once marched along the crest. Vacation cabins and campgrounds went onto lakefront terraces where people had camped for thousands of years. Even the shoreline itself has shifted. Water levels in the Great Lakes rise and fall over long time scales. Ice, storms, and changing currents eat away at some stretches of shore and build new beaches elsewhere. A small prehistoric campsite right at the water's edge might now be underwater, or buried under a dune, or hanging half eroded out of a bluff. So when we look around today and say, we only see this many pits, that's not the same as saying, this is all that ever existed. Some portion of the record is simply gone, and we don't know exactly how large that portion is. Then there are the places that are still here, but off limits for good reasons. Much of the copper-bearing country is indigenous homeland. It isn't just a landscape of old mines. It's a living cultural terrain, threaded with stories, sacred places, burial grounds, and ongoing use. Modern archaeology operates in a very different ethical world than 19th-century prospecting did. You don't just walk onto someone else's land with shovels and screens because you're curious. And there are tribal governments, legal protections, and community priorities to respect. Sometimes that means a site that could, in theory, answer a question about copper production stays unexcavated, because its primary importance is ceremonial, not scientific. Sometimes it means that research happens, but at a slower pace, under stricter conditions, shaped by what local communities are comfortable sharing. From a curiosity standpoint, that can feel frustrating. The answers seem so close. From a human standpoint, those boundaries matter more than our desire to balance a prehistoric ledger. And even when we can study a place, the story it tells is rarely singular. The same ridge can hold evidence from multiple eras stacked or interwoven. A copper mining pit dug 3,000 years ago might later collect soil and be used as a convenient fire pit by a passing hunting party 1,000 years after that. A lakeshore terrace might host an archaic period camp, a later burial, and a much later fishing site, all within a few dozen meters. When archaeologists dig, they find traces of these different episodes lying in thin bands, cutting across each other, or mixed at the edges by roots and burrowing animals and frost, trying to say, this exact feature belongs to this exact century and this exact cultural group. Can be possible in some cases, but not in every case. Sometimes we can tell that a pit was associated with old copper complex tool forms. Sometimes the evidence is more ambiguous, and all we can say is that copper was being worked in this general place at several different times, for different reasons. All of this pushes against the desire for a single, dramatic solution. It would be satisfying if we could point to one number, 500,000 tons and one destination, Europe or Mesoamerica or somewhere else, and close the file, Or, on the other side, if we could reduce everything to nothing unusual here, move along. But the ground doesn't support either extreme. What it offers instead is something quieter: scattered pits, reused landscapes, partial records, and a strong consistent signal that Indigenous peoples around Lake Superior were experimenting with, working and living with native copper over a very long span of time. Within that, there is real mystery. There are open questions about scale, about organization, about how far certain kinds of artifacts traveled. There are gaps we may never fully fill, simply because time, water, industry, and our own ethical limits have taken some pieces off the table. Mystery doesn't require us to invent a lost civilization or a vanished armada of Bronze Age freighters. It just asks us to sit with what we can see. An uneven, interrupted but still compelling record of people and a metal and lake and rock. And from time to time new pieces do surface, not from a hidden vault of secret knowledge, but from a much more ordinary place. A shelf, a filing cabinet, a forgotten box in a university basement. Those quiet places, the shelves and file boxes, have their own kind of archaeology. A student's thesis that never quite became a journal article. A regional survey published in a newsletter that went out of print in 1973. An ethnographer's notebook full of plant names and place names, written in pencil that's starting to fade. Most of what we know about the past doesn't arrive with fanfare. It seeps out of paper and microfilm and badly scanned PDFs. It comes from people who spent long, careful hours looking at small things and then tried, as best they could, to explain what they saw. In a way, this channel is just another layer in that process, a place where we pick up those small, careful pieces and turn them over again, slowly, to see how they catch the light. And since we're talking about shelves and quiet work, there is one small personal update from ours. On one of my own shelves, there's a book with many of these stories gathered between two covers. It's written in the same slow, sleep-friendly style as these episodes, and it spends a lot of time sitting with the same kind of questions we've been following along the Lake Superior shore. How we know what we think we know, where the evidence is solid, and where the gaps invite careful curiosity instead of easy answers. If you'd like more of that kind of exploration to read at your own pace, that book lives at sleepytimehistory.com. For this week, there's a discount there, a small thank you to the people who like drifting off with these strange corners of the past. It's not a set of revelations or secret files. It's more like a walk through a dimly lit archive, pulling out one folder at a time and seeing what's inside, always with the same rule we're using here. Keep the mystery, but keep it honest, and then we can set the book back on the shelf and return to the mines. Because the same questions that run quietly under those chapters are running under this story too. When we ask what happened to all that copper, we're not just asking about tons and trade. We're asking how far small communities can reach, how ideas move through landscapes, how much we can infer from what's left when most of the paperwork is gone. The bookshelf reminds us of something else as well. Knowledge accumulates slowly, and it doesn't always line up in neat chronological rows. When you look across decades of reports about Lake Superior copper, you don't see a straight line from ignorance to certainty. You see revisions, arguments, dead ends, and occasional surprises. A pit that someone wrote off as natural in the 1920s turns up in a later survey as clearly artificial. A small cache of hammer stones in an unlabelled crate finally gets radiocarbon dates in the 2000s. Oral histories recorded in the mid-20th century are reread with new attention to what they say, and what they carefully don't say, about copper and sacred places. Each of those moments is tiny. None of them by itself answers the big dramatic questions. Was there really 500,000 tons of prehistoric ore? Did it flow out of the Great Lakes in some huge coordinated operation? But together they change the shape of the mystery. early writers tended to treat the old diggings as a single coherent project. One people, one era, one purpose. The more work accumulates, the less that picture fits. Instead, we start to see layers, early experiments with native copper, when people were still figuring out what this stubborn, shiny material could do. Later periods where copper tools and ornaments were part of broader regional traditions that rose and fell over centuries. Episodes of abandonment and return, where mining ebbed in some areas and picked up in others. The bookshelf also holds studies on things that at first glance don't seem to be about copper at all. Pollen cores from wetlands, faunal lists from lakeshore camps, analyses of hearths and storage pits. Put together they whisper background conditions, what people were eating, how dense the local population might have been, whether groups were staying in one place for long stretches or cycling through the landscape with the seasons. Those details matter because they set the scale of what's plausible. A landscape with scattered mobile bands living in small camps and moving often can still produce a lot of pits over centuries. Each generation rediscovers a promising vein, digs where their grandparents dug, and leaves their own layer of hammerstones and ash. Over long enough time that can start to look like the work of a single tireless workforce, even when it isn't. But when you stack those quiet studies together, you don't see a population that looks like an industrial workforce. You don't see the kind of dense, hierarchical settlements you'd expect if tens of thousands of people were being organised to strip entire ridges in a few hurried centuries and move the metal out in bulk. You see something looser, a long, slow relationship between people and metal, shaped by changing climates, shifting social networks, and rules we can only partially reconstruct. The archives and shelves also show us how stories grow. 19th-century observers were astonished by the old pits. Some of them wrote down cautious descriptions, others added guesses, speculations and comparisons to the old world that felt natural to them at the time. Those guesses, copied and embellished over generations, became the familiar big numbers and dramatic claims. Later work, more careful and more constrained, tends to be quieter. Fewer sweeping totals, more ranges and conditionals, more "it depends." That's not as exciting on a book jacket, but it's closer to what the ground will bear. So as we keep tracing this question of where did the copper go, it helps to picture that entire invisible library behind us. Field notes and lab reports, tribal resolutions and land use plans, stories told to ethnographers, and stories deliberately withheld. Each one narrows the possibilities a little. Each one makes certain dramatic solutions harder to defend, without erasing the fact that there is still something here we don't fully understand. The bookshelf, in other words, doesn't close the mystery. It just changes its shape, making it less about missing mountains of metal and more about the quieter, harder question that remains. Given what we actually see in the pits, in the artifacts, in the soils and in the written record, what scale and pattern of copper working best fits the evidence? That's where we'll go next. When you zoom all the way out, past the headlines and the book covers and the arguments on message boards, there are a few things that almost nobody in this field disputes. People around Lake Superior were working native copper thousands of years before the Bronze Age kingdoms of the Mediterranean rose and fell. They knew how to find it, how to test a vein, how to knock metal out of bedrock with stone hammers and fire. They knew how to heat and hammer and anneal it into tools and ornaments. They developed distinct ways of shaping it that belonged to that region and to those cultures. There were real mines, not just chance encounters with shiny pebbles, pits with spoil heaps, hammerstones worn down to stubs, charcoal lenses that give us dates. There were networks of exchange that moved copper far beyond the immediate shoreline, out into the wider Great Lakes and beyond. There were indigenous traditions that treated copper not just as a material, but as something with power, with rules around how and where it could be taken. That's the solid ground. What lies on top of that ground and still shifts under our feet are the bigger questions people tend to latch onto. How much copper, in total, did those communities actually remove? Over what span of time? How widely was it distributed and in what forms? When we talk about missing copper, missing compared to what? Part of the difficulty is that all of those questions are tangled together. If you assume a short, intense mining boom with a large coordinated workforce, you end up with very big totals that don't seem to match the archaeological footprint of settlements, burials, and everyday life in the region. If you assume a long, intermittently used landscape, mines opened, abandoned, and reopened over millennia, the same number of pits implies a much slower trickle of metal. The mines themselves don't tell us, on their own, which of those pictures is closer to the truth. A pit that looks deep and impressive in the forest today might have taken a few concentrated seasons, or could have been worried at, on and off by small groups over centuries. A scatter of hammerstones could be the toolkit of one busy year or a palimpsest of returns we can't easily separate. When people try to estimate total output, they have to make assumptions about all of that: labour, methods, continuity of use. Change the assumptions and the tonnage moves up or down by orders of magnitude. That's why responsible estimates tend to come with wide ranges and careful qualifiers, rather than single dramatic numbers. Timelines are similarly soft around the edges. We have radiocarbon dates and relative sequences that anchor certain episodes. The old copper complex, later woodland period use, 19th century reworking of ancient pits. But between those anchor points are long stretches of time where activity could have risen and fallen without leaving a clean, continuous record. Distribution is even trickier. Copper corrodes. It gets recycled. A broken tool can be cold hammered into a new one. Metal that left superior as a utilitarian blade might end its life as a tiny ornament, melted or hammered so many times that any microscopic clues to its origin are scrambled. Trade items can pass through many hands before they land in a site we happen to excavate. Most will never be excavated at all. So when people point to the gap between impressive mining scars on the Keweenaw and a relatively modest tally of artefacts in museum drawers and site reports, there are two broad ways to look at it. One is to say there must have been something big we're missing. A large-scale export trade, perhaps, that carried most of that copper into distant societies where it was melted down, reused, and eventually lost in contexts we haven't recognised or connected back to Lake Superior. Within that line of thinking you can place cautious possibilities and more speculative ones side by side. It might be that Great Lakes copper moved farther into North America than we currently see in the record, and that we simply haven't found or chemically tied enough artifacts back to their source. It might be that some reached Mesoamerican or Caribbean networks in small amounts, piggybacking on long chains of exchange that are archaeologically faint, and then farther out on that spectrum are the claims that it fueled Old World Bronze Age economies on a scale comparable to their own local sources. Those claims are at this point much harder to square with the isotope data, with known Bronze Age ore fields, and with the lack of clear Lake Superior fingerprints in well-studied Old World assemblages. They remain possibilities in the logical sense, you can imagine them, but they aren't supported in the evidentiary sense. The other way to look at the apparent gap is quieter. You start with the idea that over thousands of years, even small, loosely organised communities can move a surprising amount of material, especially when they keep returning to the same favourable spots. You add in the fact that copper was embedded in ritual and social life as much as in everyday tools, so a great deal of it may have ended up in contexts we don't routinely dig, or that descendant communities regard as off-limits to excavation. You remember that metal gets recycled, especially in societies where it isn't abundant. In the picture there is still missing copper, but it isn't missing in a dramatic sense. It's missing the way most artifacts from deep time are missing, dissolved back into the soil, sitting in unexcavated sites, lying in riverbeds, reworked into other things, hidden in places that are not ours to look. Between those two broad interpretations, there's space for many smaller possibilities and for revisions as new data comes in. Someone refines sourcing methods. Another team finds a cluster of old copper artifacts far from any known source. Tribal nations choose to share or to keep private parts of their own copper stories. The picture shifts again, slightly. That, in a way, is the real mystery that remains. Not a single, neat solution about where 500,000 tons went, but the slower, less cinematic puzzle of how small human groups, over very long periods of time, interact with a particular landscape and a particular material, how they weave it into their tools, their trade, their ceremonies, and their stories. How much of that can be reconstructed from pits and sherds and lab reports, and how much will always belong to the people whose ancestors lived there, and to the land itself. Standing on the modern shoreline, it's tempting to want closure, a final total, a definitive map of where every pound of copper ended up. The evidence we have doesn't really lend itself to that kind of ending. What it does offer is a different kind of satisfaction. We can say, with some confidence, that long before industrial smokestacks rose over the Keweenaw, people were here, learning this metal. The old pits and hammerstones are their signatures. We can say that later stories about lost races and secret Bronze Age armadas tell us more about 19th-century imaginations than about those earlier miners. We can set those stories back on the shelf, not with contempt, but with the understanding that they were guesses made with less information than we have now. And then we can let the remaining questions stay questions for a while. Not as gaps to be hastily filled with the most dramatic explanation available, but as open spaces where curiosity and respect can coexist. Respect for the archaeological record, which is always partial. Respect for Indigenous histories, which include knowledge that was never meant to be extracted and catalogued. Respect for the deep time of that lakeshore, which has seen many different ways of being human. If you imagine the mines at night, with the lake breathing quietly below the ridges and the stars turning over the water, the mystery feels less like a locked box and more like a horizon. You don't have to reach it. You just have to sit with it for a while and let it remind you how much of the past is still out there, intact, in the dark. And with that we can leave the copper where it is for tonight and let the waves and the wind have the last word. If you're still awake, or drifting somewhere in between, you've now spent a while wandering through those pits and shorelines and stories. You've met the parts we can point to with some confidence, and the parts we have to hold at arm's length, with a quiet maybe. That's really where we have to leave it. The Lake Superior copper mines don't resolve into a twist ending. They don't hand us a secret map that ties every old world sword and plough back to one stretch of rock. What they offer is a slow, complicated, very human story. People learning a difficult material over a very long time in a place that asks a lot and gives back just enough. The numbers we see in headlines, the missing tons, the grand export schemes, they sit on top of a much softer foundation of assumptions. Change those, and the picture tilts. The mines are still there in the forest. The artifacts are still in the ground and in the water and in the care of descendant communities. Our interpretations move around them like light shifting on the lake. So for now, the honest answer is also the gentlest one. We don't know exactly how much copper was taken, or how far it ultimately travelled. We can trace some of its paths. Others fade into ordinary life, into tools that wore out and were remade, into offerings returned to the earth, into stories that don't belong to archaeology at all. If you'd like to help this kind of quiet, careful history keep finding its way to people who enjoy it, you can tap the buttons that everyone on this platform has to mention. Liking the video, subscribing to the channel, and leaving a comment all tell the algorithm that there's an audience for slow mysteries and unsolved questions. And if you do feel like leaving a comment, I'd love to know where you're listening from. A city by salt water, a landlocked town somewhere near the Great Lakes themselves, or halfway around the world. It's strangely comforting to picture all the places these stories are being heard. If this sort of deep time wandering helps you sleep, or keeps your curiosity company late at night, you might also like the book I've put together about prehistoric secrets and the quieter side of the human past. You can find it at sleepytimehistory.com. For now, let the shoreline go dark again. Let the old pits fill with leaves and snow, and the copper stay hidden under stone. Let the questions settle in beside you, not as something to solve before morning, but as companions for the long, slow work of wondering. Good night, sleep well, and keep the questions close.